In the last video, we have seen insertion in a binary tree. Now we will see how to delete a node from my binary tree, correct? So this is my binary tree. It is following all the properties, okay? Now what we have to do is we have to delete a node from it. Now there are three cases in the deletion from the binary tree, okay? Not the binary tree, but the binary search tree, that is BST. There are three cases. And why are these cases? We will know, okay? I will tell you in just few minutes. So the first case is not to be deleted is a leaves node. So if I want to delete 15, so here if I want to delete 15, I can directly delete 15 without disturbing any property of my BST. Okay, because of those properties that in the left side the lesser element will be there and in the right side the greater element will be there. Therefore the deletion has to be taken care of. Okay, so therefore in case of deletion we have to take care of few points, correct? So 15 can be directly deleted, 30 can be directly deleted because they are leaves and there is no node below them, correct? So they do not have to take care of anything, so they can be deleted directly. Simply delete the node. If I want to delete 70, I can directly delete 70 from my binary search tree. Next case is node to be deleted has a single child. If the node that is to be deleted has a single child, for example, I want to delete 25. So 25 only has one child, that is 15, and it does not have a right child. Okay, it does not have a right child. It only has a single child. So in this case, replace the node with a child node. So replace this 25 with 15 and delete this 15 and delete this 15. So what you have to do is when we have a single child, either a left child or a right child, so copy this one here, so 15 will be copied here and delete the 15th node, correct? So we can do this. This is simple. The next step is, that is the third case, and that is the most important case. The third case is node to be deleted has two children. For example, I want to delete 15, so it has two children. Or I want to delete 50 here, the root node, it also has two children. One children is 25, the second children is 75. Rest are grandchilds, not childs. So 50 has two child, 25 and 75, correct? So if I, for example, I want to delete 50, so what are the steps I want to take care of? So the first step is find the in order successor. Now what is an in order successor? Just find the in order of this tree. What is the in order of this tree, and whatever comes after 50 will be my in order successor. Whatever comes after 50 will be my in order successor. So just write it down. I have explained you how to find an in order in a binary tree. The same method will apply for a binary search tree. So we will start from here and we will go to down, okay? And whenever a node is encountered for the second time, then we will print it. So this is the first time for 50, this is also a first time for 25, then we come down here, this is the first time for 15, correct? We go to its left, there is nothing, we go to its, we come back, so this is the second time. So since this is the second time, I will print 15, I will print 15. Now go to its right, there is nothing, and this is the third time, this is the third time. So for post order we will print this. So 25, now it is the second time for 25, just simply print 25 and move ahead, move to the right. First time for 30, here it will come to its left, and the second time for 30, second time for 30, then come here to its right, then move back. This is the third time for 30 and this is the third time for 25, so on. What you have to do is, now this is the second time for 50, so print 50, so on. You have to print the pre-order for this. You have to print the pre-order for this. So 15, 25, 30, 50, next will be 70, next will be 75, and next will be 85. So who is the pre-order successor of 50? Pre-order successor of 50 is 70. So you have to replace 50 with this 70. You have to replace 50 with this 70. Okay, so this 50 will be replaced by this 70, that is here 70 will come and this 70 will be deleted, this 70 will be deleted. So now when 70 is replaced, 50 is replaced by 70, see, are the properties satisfied? See this, these all terms are less than 70 and these all terms are greater than 70. So yes, property is satisfied. Also what you can do is you can find the pre-order predecessor. So 30 can also replace 50, 30 can also replace 50. So if I replace 30 with 50, just delete 30 here from here. So as you can see, these all values are lesser than 30 and these all values are greater than 30. So no problem here also. So either use 30 or either use 70, in order successor or in order predecessor. And now you can notice that in BST my in order gives ascending order. In BST my in order gives ascending order. If someone gives you a BST tree and tells you to find the in order of it, just write the ascending order of the nodes. Just write the ascending order 15, 25, 30, 50. As you can see, it is an ascending order. Okay, this is just a small point which is very helpful in the exams. Okay, this lets you solve the exam very fast, question very fast. So you know the steps now. What are the steps? Find the in-order successor or in-order predecessor. Then what you have to do, you have to simply replace that with the node you want to delete. Okay, and then delete the in-order predecessor or successor. Okay, this is very simple. So now let me just revise what are the points that we have seen till now. So here, this is the first example. So what will happen is, it's very simple. First, what you have to do, you have to check whether the root is null or not. Okay, every time what you have to do, if you want to delete 30, if you want to delete 30, so first you have to reach 30 to delete it. Okay, you cannot directly delete it, you have to reach 30. And how will you reach 30? It's very simple. Check for 50. If it is less than 50, go to the left. If it is greater than 50, go to the right. 30 is less than 50, so go to the left. Correct. Check whether it is equal to 30, less than 30, or greater than 30. Now why equal to also? Because now we are deleting, we are not inserting. Okay, in insertion duplication is not allowed. Fine. Now if you want to delete 30, you want to check whether this is 30 or not. Therefore equal to will also come. So check here also for equal to. So here it will check for equal to. If it is not equal, so check for left side and check for right side whether it is less than or greater than. Since it is greater than, come to the right side. Now check whether it is equal to. Yes, it is equal. Whether it is leaf. Yes, it is leaf. How can you check if it is a leaf or not? You can simply check left is also null and right is also null, so yes, it is a leaf. Okay, and you can directly delete it, you can directly remove it. Simple, it's very simple. So for the first step, check whether the node is null or not, that is the root is null or not. No, it is not. Then the second step is very simple. Check whether it is less than, greater than, or equal to. There are three conditions. Check less than, greater than, or equal to. Okay. Now what you have to check is the second condition. The second condition is whether it has one child or two child. Okay. For example, I wanted to delete 25. So what I will do is I will check whether 25 has one child or two child. How I can check? It is very simple. Check the left one and check the right one. Node dot left, node dot right. If one of them is null, that is, if 25 dot left is null or 25 dot right is null, in this case the right is null, so you can simply say that it only has a single child, and then you have to perform this operation. Okay, this is a simple operation. In the last one, what you have to do is you have to do all the three steps above, that you have to check whether it is null or not, check for the left side, check for the right side, and also what you have to do finally, you have to check after left and then right, you have to check whether it is equal or not. And if it is equal or not, now for the root it will be equal, that is 50. If I want to delete 50, it will be 50. After that you have to write a function to get you the element, which element? That is the in-order successor, or in-order predecessor. Write a function, write a method to get you this. And how you will get 70? You always know that the in-order successor, that is 70, go to the right side, and in this tree the leftmost element will be your in-order successor. Go to the right side, and in this tree the leftmost element, okay, the leftmost element will be your in-order successor. If 70 is not here, then 75, it is the leftmost element, correct? So go to the right side, and in the right subtree the leftmost element is your in-order successor, or in case of in-order predecessor, go to the left side and the rightmost element is this, correct? So don't get confused, it is very simple to find the 70. It is very simple. I will show you in the code. Okay, then replace it with this 70 with this, and just delete this one. It is done. So this was deletion from BST. Okay, now I will write a code for the deletion of BST. What I have to do, I have to check whether it is null or not. If it is not null, check for the left side. If it is not in left, check for the right side. If it is not null, not left, not right, means it will be equal to the node. Okay, if it is equal to the node, check whether it has one child or two child. Okay, if it has one child or two child or no child also, so check for all the three conditions. If it is no child, then simply delete it. If it has single child, then do the second step. If it has two child, then do the third step. So this is completely my deletion from BST. I hope you understood it. It is really simple. You can simply do this. Okay, I urge you to write a code for this. You can simply write a code for this. Think a little bit, and you can write a recursive code for this one. Okay, here also in recursion we need two things, that is a node and a key to delete. Okay, so what key will represent this time? It will represent the delete. And what do you think a node will represent? A node will help to check whether it will go to left or whether it will go to the right. Okay, so just think a little bit, try to write the code, and then cross check the code with my code. Okay, just pause the video and try to write your code by yourself. Now in my BST methods class, now I will simply write a code for the delete, so void delete. Now it is the same as above, that is insert. First we will, from the main, we will just simply get our key, the key that we want to delete. Okay, and from here I will call another function for recursion deletion. Okay, recursive deletion. So root delete using recursion, delete recursion, and here simply I will simply say root and the key. Okay, this is the same as I've explained you for insertion also. Fine, so you can say that this delete node recursion. Okay, not delete the node recursively. And then what we will do, we have a node delete node recursively and a node to store my arguments. Okay, and integer key. Okay, fine. So this is done. Now tell me the steps. Now you know the steps. I have told you the steps. There are basically 4 steps to do in this one. Okay, so we have to apply if else conditions. So what will be the first step? Just think about it. Just tell me what will be the first step. The first step is simply if node equal to null. So if it is null, then simply return it. Then simply return null node. This is done. So it is null, so it will return a null. Okay, now if it is not null, then what we have to do? Now if it is not null, then we have to check whether to go to right or we go to left. Now you know all the steps. I have explained all the steps. So first is checking null, then you will see if it will go to left or whether it will go to right. So just pause the video here. Also you can pause the video if you haven't done this before, so you can do this now. So key is less than not dot data, not dot data. If key is less than not dot data, if it is less, where we have to go? Just think about it and tell where we have to go. If the key is less, it is simple, not dot left. If the key is less, we go to left of it. So it is equals to delete node recursively, not dot left. So it will go to the left side tree and it will perform the same operations again. It will go to the left subtree and it will perform the same operations again. Else if the key is greater, so tell me if the key is greater, then where we will go? We will simply go to the right side. We will simply go to the right side, check with the data and just go to the right side of it. So not dot right and equal to delete recursively and go to the right subtree and perform the same operations on the right subtree also. Fine, till you find the key. Now I have checked for 3-1, if the node equal to null or not. If the node is less than key or if the node is greater than key, then we have checked. Now if all these are false, then the only remaining one in else is it is equal. It is equal. Now if it is equal, now what we have to do, we have to check whether it is of a single child or it contains 2 childs. Correct? So let me check if it contains a single child or it contains a 2 childs. Okay, 2 children. So if node dot left equal to null, so in this case what it is, that is left is null, so return the right one. Return node dot right, node dot right. Correct. So what is happening here? Left child, we do not have a left child, so we will simply return our right child. Correct? Else if we do not have a right child, then what we will do? Just think about it. What we will do? You know what we will do? We have just did this. If the right child is not there, then we will simply return our left child, node dot left. Correct? Now if both the childs are present, that is both the conditions are false, then what we will do, we will find our minimal element, or we will find our element that is from the right side and the leftmost element. From the right side, the leftmost element, that is the in order successor. We will find in order successor. So node dot data, in the data I will copy whatever the in order successor is. What I have told you how we will do this, it's very simple, that we will find the in order successor and I will copy it in the node of data. I will copy it in a node of data and I will delete the in order successor. Correct? So we are doing this. Now node of data will contain the in order successor. For this I will just use a function, for example minimum value. Why I am using the term minimum here? Can anyone guess why I am using the term minimum here? So those of you who guessed, you can see this one here is that we are 75, we are going to the right subtree. This 70 is the minimal element. In the right subtree, the leftmost element is the minimal element. Now I will be showing a iterative code here. In the next video we will see how to find the minimum and the maximum element of my tree or any of the subtree using recursion. Okay, so this time I will show you a iterative code. So in the right, I have to come to a right subtree. Correct? And this right subtree, the leftmost element is the minimal element and the rightmost element is always the greatest element. So this is the property of BST. Okay, now what I have to do, I have to calculate this. I have to write a code for this. Okay, just let's write a code for this. So it will return an integer. It will return an integer, that is the value of the key. and I have a node and a node. So can anyone write this code by your own? Just try to write this code by your own. So int, for example, min value, that is an integer to store the min value, variable to store min value, node dot data, node dot data. So currently what it is? Currently it is 50. Currently it is 50. I want to delete 50. For example, I want to delete 50. Okay. For example, I want to delete 25. So currently it is 50. Currently it is 25. Anything which I want to delete, currently it has that value. Correct. So node dot data is currently 50. Next, what we have to do, while. Now what has done is, sorry, I made a blunder here. We are passing node dot write. So currently it is actually 75. If we are deleting 50, currently it is actually 75, not the value of the node. Okay, sorry for that. This is node dot write, correct? I am passing a node dot write here. So node is 50 and passing the write, that is 75. So yes, the min value is not 50, min value is currently 75. Now I am at 75. So now what I have to do, I simply have to go left and left till I found the leftmost element. Till I found the leftmost element, I am to go left and left, and once I found the leftmost element, I will just simply copy it. I will simply copy it. And how you will find the leftmost element? Just check. If there is no left child, that is the leftmost element, correct? So there is no left child for 70. So 70 is my leftmost element. So while node dot left is not equal to null, So while node dot left is not equal to null, what you have to do? You have to simply do two things. Now think what you have to do. Just two steps. If node dot left is not equal to null, there are just two steps to follow. Now simply do what you have to do. We are at 75, correct? We are at what? We are at 75. So node dot left is equal to null or not? No, it is not equal to null because 75 has 70 in the bottom of it, correct? 75 has 70 to the left of it, so it is not equal to null. So if it is not equal to null, we have to update our value, that min value, which will be equal to node dot left of data, correct? Node dot left of data. So simply write that down, node dot left of data, node dot left of data. So what is node? Node is 75, node dot left is 70, and the data is 70 there, correct? So we will simply do this and we will update the node to node dot left. Now my node became 75. Now when this again function calls, this again loop will iterate. Now node dot left is null. Why? Because the 70 is the leftmost element and I have to return this leftmost element. Okay, so I will simply return my node. I will simply return, not node, I will simply return the min value. I will simply return the min value. Now this min value will be stored in node of data. So what I have done is I have copied the 70, that is the minimum value on the right subtree, to 50. Now 70 is copied to 50. Now what I have to do? I have to delete this 70. What I have to do? I have to delete this 70. So to simply delete this 70, what we will do is node dot write equal to delete node recursively, node dot write, comma, node dot data. Okay. So what we are doing is, now what is node of data? Node of data is currently 70, correct? So in our own deletion function, we are passing the key value as 70. So what we are saying is, just check in the right side of 50, that is the check in the right side of now 70, that whenever you find a 70, delete that node. Wherever you find a 70, and delete that node. And the point is that 70 will always be a leaf element. Okay, the 70 will not always be a leaf element, but it will not be a third case. It can be a second element, second case also, but it is easy to delete. It is very easy to delete. Fine. So node dot write and node dot data. So node dot data is currently 70, and he is saying that whenever you find 70 on my right hand side, just delete it. Just delete it. Okay. So what is saying that I am now here. So whether you find me again on my right hand side, that is on the right hand side, delete it. Delete that node. Okay, what we have to do, that is the third step. Delete the inode or successor. So this is what we are doing. So just return the node in the end. Just return the node in the end. So this is done. So this is done. This is my deletion. So what we have performed in deletion is, now tell me what we have performed in deletion. What we have did. Now I know you know. It is easy. So first step is check whether the node is null or not. Okay. The second step is whether the second step is, if the node is not null, go to the left side or go to the right side, or this time it can be equal also, correct? So if you go to the left side of it, what you have to do, you have to delete from the left subtree, or if you go to the right side of it, you have to delete into a right subtree. Okay, this recursion function will take care of this. Next one is, the next condition, if These are equal. If you find the node, if you find you have to delete 25, you come to the left and you found it 25. Now what you have to do is you have to check whether it has one child or it has two child. If it has one child, then this is the code. If it has two child, then this is the code. What you have to do, you have to find the in-order successor for it or in-order predecessor. Now you can write the code for in-order predecessor also, correct? Then just copy it and just delete it. This is very simple. Okay, this is deletion for my BST, correct, binary search tree. Now from the main method, what I have to do is I have to simply call it. Let me just call it. It's not hard, it's very easy. Okay, just you have to concentrate a bit. So tree.delete, for example, I wanted to delete 25. Now this one is my big tree. This is not a small tree. Okay, this was the tree we have used in insertion, correct? So if I want to delete 25 here, what I have to do, I have to simply delete it and system.out.println /n and call the preorder again. Preorder tree.root. Now there is a question here. The question is, once I print the preorder of this one, so what will be the preorder of this one? I have explained this in the last also. Okay, so yes, here it is. So this is the preorder, correct? And I want to delete 25. Now tell me which element will replace 25. Which element will replace 25? What I am doing is I am using preorder successor, not predecessor. So what is the preorder successor of 25? Just think about it. Okay, not a pre-order successor, in-order successor. Just think about the in-order successor. What will be the in-order successor of 25? Just think about it. I have told you that in a BST, the in-order sequence is nothing but my ascending order. So what will come after 25 in ascending order? It will be 30. So 30 will replace 25. So what should be my answer? My answer should be 50, then 30, 15, 10, 23. 30 will be deleted from here. After 23, I get 46. So this should be my sequence. Okay, you should have been able to answer this. If you haven't, just watch the video again because this is very important. Fine. What we have done is we have simply deleted 25, and here in order successor of 25 is 30. So 30 will simply replace it. It is very simple. Okay, so let me do it. So if I run the code now, the answer should be 50, 30, 15, 10, 23 and 46 after that. So as you can see, it's magic. So 15 and 30, so 25, 30, 25, 30, correct? 25 is deleted and 30 replaced it, and from here 30 is deleted. So this is what I was talking about. If I again add 25, let me add 25 this time. Okay, one second. I'm again adding 25 and using the same thing again. So let's do some experimentations now. So if I add 25 again, so what do you think? Will I get my new tree? Will I get a new tree or will I get a previous tree again? So you will get a new tree. Why you will get a new tree? Now 30 is in the place of 25. So 25 is less than 30. So it will be on the left side of 30. It will be on the left side of 30. Now if you run it, you will see that 25, we do not get the same tree again, but 25 is somewhere here. Okay, 25 is somewhere here, which is actually on the left side of 30. If you draw the tree, you will get that it is on the left side of 30. Okay, so this was pre-order. This is just a pre-order sequence because we have written a code for pre-order. Now what if I want to delete anything else? So tree.delete, just delete for this time for fun. Let's delete the root this time, though I have told you the answer for the root. No, don't delete the root. Delete what you can delete 85. Delete 85 and tell me what will replace 85. Okay, this is very simple. Delete 85 and tell me what will replace 85. So here it is. I am deleting 85 and I am printing. Okay, I hope you know what will replace 85 and the answer you will give is correct. Okay, let's see what will replace 85 in this one. So if I delete my 85, as you can see, 90 replaced 85. 90 replaced 85. Okay, I hope you know why 90 replaces 85, because in order successor 85 successor is 90, therefore 90 replaces 85. So this is how you can experiment differently with the code. Okay, you can, if you have any doubt, just try to delete, insert many things and you will understand it correctly. So this was deletion in binary search tree. Next what we will see is we will see how to find the minimum element. We have seen this actually, how to find the minimum element. We will see it recursively, how to find the minimum element, how to find the maximum element. Also we will see how to find any element, if I want to find that 70 present or not, or if you want to find 23 is present or not. if you want to find 15 is present or not in my tree, then you can use that function that we will create in the next video. Fine. So I think I should stop this video now. It's been too long. But what you have to do is you have to write this delete function yourself. Okay. What we did, we first found that node is null or not, then check on the left side, check on the right side. If it is equal, check whether, if it is equal, check whether a single child is present or two childs are present. If a single child is present, simply return the other child. If the two childs are present, just find the inode successor and delete that, copy that and delete that. It is very, very simple. Okay, copy and delete. See, 90 is copied in the place of 85 and 85 is deleted. Okay, 90 is deleted at the end. So this was very, very easy. So this was deletion, and next what we will see is I have told you. So meet you in the next video.